Okay, so this video is going to be about a couple new functions that we're going to be using in the class. And the first one is the rectangle function. And the next one is what's known as the delta function. Okay, so let's start with the first one. So the unit rectangle function is, I'll draw it for you. Actually, in this form, it's a square, but that's just this one particular form. So this is rect of t. We denote it rect, the rectangle function. But more generally, if I took this rectangle function and I moved it somewhere else, or I stretched it along either axis, we would still call it a rect function because it looks like a rectangle. This is just the particular one we call the unit rectangle function, the one we give this name rect of t. So I could shift it. I could have, like rect of t minus 5. I could scale it. I could have like 5 times rect of t. I could combine these. I could time scale it. I could have rect of 3t. So I can do all these manipulations to get other rectangles, okay, in all different locations. This one is just called the unit rectangle function because it's our standard one we call rect of t, and then all the other ones we can transform this one to get. Okay, so as a formula, rect of t, what does it look like? Well, it's either 1 or 0. Okay, it's 1 if the absolute value of t is less than a half. You can see if we're in this range, it's 1. And it's 0 if absolute value of t is greater than a half. Okay, and you might ask, well, what happens at a half? And the point is we never really worry about those points. They're not going to play a role in this class. They can really be whatever you want. We just want there to be some range where it's 1, some range where it's 0. You could take at a half, you could take it to be 1 or 0 or whatever you like. We'll design everything in the class to make sure that that ambiguity never comes into play. Okay, so you don't have to worry about that. All right, so this is the rect function. Okay, and now what are we going to do with this? Well, we're eventually going to get to this concept of the delta function. And the way we get there is what we're going to do is let's make a sequence of taller and thinner rect functions. And we're going to make sure all of them have area equal to 1. Okay, so it turns out that's going to be a property we want. Okay, so we'll start off with one that's, not that tall, not that thin. And we're going to have its width, its lower limit be negative t naught over 2, its upper limit t naught over 2, and its height is 1 over t naught. Okay, so you can see that if I calculated the area, what's the width? Well, the width is t naught, and the height is 1 over t naught. And so the area here is 1. That's what we wanted. And now I'll take this function, okay, and I'll draw it a few more times. And each time I'm going to let it get taller and thinner. Okay, so maybe the next time it's here, maybe the next time it's there, maybe the next time it's like this. Okay, so I always want the area to be 1. Okay, and in every case, I'm going to go from negative t naught over 2 to t naught over 2 and have height 1 over t naught. Okay, just do like dot, dot, dot. And you can see still here by the same calculation, the area is still 1. So the area is always 1. And you can see that this sequence of rect functions is getting thinner and taller. Okay, and the formula for any of them, well, what's the height? The height is always 1 over t naught. And then I'm just going to scale it by t naught in the time argument. Okay, so you can see if I plug in t naught over 2 for t, okay, the t naughts cancel and I get 1/2. And that makes sense because you can see here 1/2 is the place where the right edge of the rectangle comes down. And that's what's happening at t naught over 2. Same thing at negative t naught over 2. Okay, so this is the equation of all of these rects. And as we go to the right, that t naught parameter is just decreasing. Okay, t naught, I'll say decreases as we go to the right. Okay, and so these rects get thinner because that range on the t-axis is getting smaller, t-naught's decreasing, and they get taller because the height is 1 over t-naught. Okay, so this is the picture to have in your head, and then I'll write in the limit, and I'm going to put limit in quotes because what we get at the end is not even really a function. I'll talk about that in 1 second. But in the limit, as t-naught goes to 0, this function becomes a delta function. And we denote it delta of t. So that's a Greek delta. Okay, Greek delta of t. One more try. There we go. That's a good one. Delta of t. And some people call this the Dirac delta function. Yeah, we're just going to call it the delta function. And so we have this delta of t. This is a Greek delta. And it's going to be this, in quotes, limit. T-naught goes to 0, 1 over t-naught, rect t over t-naught. Okay, so it turns out that there's this whole branch of math called distribution theory, and this delta function is actually what's known as a distribution. It's not really quite a function because if I were to take this sort of magical limit, what's going to happen? Well, this delta function really equals 0 everywhere except right at the origin, in which case it sort of equals infinity, right? If I let t-naught go to 0, this height here is going to go to infinity. And that's not really a function because functions are supposed to take on, in this case, if it's a real function, real number values, infinity isn't actually a number. It's like an added symbol we add to the real number. So this isn't quite a function. And on top of that, we say that this delta function has area 1 because all of these functions that, we looked at the sequence of these rects all at area 1. So it's kind of a weird limit. It's kind of this thing that we work with and are able to get results with. So it works out. It's okay. And in a future video, we'll go into more properties of the delta function, but it is not quite, a limit in the typical sense. That's why I put it in quotes. Okay, so this is an impulse at t equals 0, and I'll show you how we draw it. Drawn like this. Okay, so we draw some axes, and then we draw it with these 2 vertical bars like this, and then a triangle on top. Okay, so this is delta of t. And we typically denote its height by its area, okay, which is a little weird. And we'll, again, in future videos, we'll talk much more about the delta function. But I'll just tell you for now, we denote its height, which is really infinity there. But when we draw it, we denote its height as its area, which is 1. Okay. So it's a strange function, and we'll deal with it more in the future, but I just want to introduce it for now because we'll need it in the next video. And so what's it really saying? It's sort of like an impulse right at t equals 0. It's like a lightning bolt. Comes down right at t equals 0, or like you could think of it as a clap, like you clap your hands, or in experiments, actually, people sometimes simulate this with a balloon pop right at t equals 0. Okay, so it's sort of like this bolt of energy right at that point. Okay, and that's what a delta function is. Sometimes we call it an impulse function because, like I said, it's kind of putting an impulse right at t equals 0. And we'll be able to shift this delta function around and do various things like that too. So we'll treat it as a normal function, but it's going to have some strange properties that we'll cover in a new bit in a future video. Okay, so that's all I had for this one. I will see you in the next one.